Hello everyone, my name is Mo. Today I'd like to talk about our work on building a verified concurrent file system. File systems are important, they are widely deployed. However, they are too complex to be bug-free. Verification is a promising approach. It formally proves the implementation meets the desired specification. Previous work on concurrent file system verification has made tremendous progress, including our prior work at RefFS, which is a verified concurrent file system with linearizable interfaces, and the DAISY-NFS, which ensures the quality safety of a concurrent file system. Unfortunately, this work only verifies safety properties. Namely, bad things never happen. They still do not guarantee liveness property. Namely, good things eventually happen. Therefore, this work precisely targets this issue. We want to verify the liveness of a concurrent file system. By liveness, we mean every operation of the file system terminates under the assumption of file scheduling. To understand the scale of the problem and the challenges, we perform a study of termination bugs in the Linux file systems. We found that concurrent bugs, more specifically deadlocks, are dominant, accounting for about 80% of all termination bugs. In a deadlock, a thread becomes blocked, waiting for an action that never happens, and none of involved threads can make progress. In this talk, we will focus on the verification of deadlocks given their prevalence. Now, let's look into deadlocks. To understand why deadlocks are so difficult to avoid, we make the following observations. The first observation is that about half of deadlocks involve ad-hoc synchronization, which is often not supported by existing deadlock analysis tools. An example of ad-hoc synchronization is the following busy waiting loop. The current thread busy waits for an action of another thread. The waited action may be the completion of a transaction, flushing of dirty inodes, or other custom synchronization points. Once the waited action is fulfilled, the condition in the if statement becomes true and the while loop terminates. Unlike patterned lock-on-lock primitives, such ad hoc synchronization has no specific pattern and can be hard to analyze. Our second observation is that most deadlocks involve nested waiting, where a task A waits for another task B, and the task B also waits itself for some task. Such nested waiting introduces complex dependencies of progress, which is prone to deadlocks. For instance, the rule for removing an inode is to first acquire the parent lock, and then hold the parent lock to acquire the child. Suppose task A requests parent lock, and the parent is owned by an unlink operation, so it waits for the unlink to release the parent. But the releasing parent may get blocked and wait for another task B releasing child first. A deadlock happens if there is a circular wait for task A somehow. To prevent deadlocks, it is necessary to specify a global order of wasteful dependencies, but such a specification is still absent for concurrent file systems. At last, we observe that in about 8% of deadlocks, the waiting order cannot be known statically. For instance, the previous parent-child waiting order is dynamic. At the initial stage, the release of A may wait for the release of B. But when we move around inodes so that B becomes A's parent, the wasteful dependency between A and B becomes opposite at the new state. Such dynamically changing waiting order is challenging to formalize and reason about. In recent years, much theoretical work has made progress to address these challenges. Unfortunately, this work has only limited support for dynamic waiting order. Besides theoretical limitation, they have only been applied to small examples, but not anything near a file system. Many of them have no executable implementation or mechanized proof. As a result, modular liveness verification of a concurrent file system remains an open problem. In this work, we have addressed these challenges and made the following contributions. We propose a framework called MOLI for verifying concurrent file systems. We have applied MOLI to verify a file system called RefFS, which is the first to guarantee both safety and liveness. Furthermore, we apply our methodology to perform a protocol-level proof of the directory working rules of Linux virtual file system. Now, let's first look into our methodology. The high-level idea is to represent the wasteful dependencies in a system as a wasteful graph. When a thread gets blocked, it waits for an action of another thread, which we call unblocking action. The unblocking actions could be releasing the lock or fulfilling some ad hoc actions. They constitute the vertices of the graph. There may also be wasteful dependencies between these actions, which we draw as directed edges. The core idea is to ensure the wasteful graph is acyclic, such that unblocking actions eventually happen without getting into deadlocks. Consequently, these threads become unblocked and terminate on their own. To formally capture cyclicity, we require users of our framework to layer the unblocking actions in their system, such that an action waits for only a higher numbered one. For instance, for the following wasteful graph, one may leverage the topological order to assign layers. To capture dynamic waiting order, one should define the layer of an unblocking action as a function of state. For instance, in the left file system state, the release of A waits for the release of B. So A's layer is defined to be less than B on this state. While in the right file system state, their layer relation is defined oppositely to reflect their new wasteful dependency. Despite such dynamically changing waiting order, layers enforce that for each state, there is a global order of wasteful dependencies, so deadlocks are never possible. We encoded the wasteful graph methodology into a framework called Molly. Molly allows for proving a concurrent file system in the quark proof assistant. Molly consists of the following parts: a quark-modeled C implementation, a user-defined specification, and a set of inference rules which guide the users to manually perform the whole-style verification. We have proved soundness of our program logic, so once users finish the proof, the safety and liveness of the implementation is formally ensured. Now, let's talk about how to apply Molly to a concurrent file system. In a file system, the rule for concurrent access of inodes is to protect each inode with its own fine-grained lock. To prove liveness, one task is to define the wasteful order between inode locks. For simplicity, let's focus on only two orders. The first order is the parent-child order. To encode this order, the layer of an inode can be defined as the distance from root. Namely, the root has layer 0, and after each hop, the layer increases by 1. This definition accounts for dynamic waiting order because layers are always computed dynamically according to the state. The wasteful graph so far is acyclic because it follows the file system tree. The second order that we focus on is in rename. Simply speaking, what rename does is to move an inode from its old parent to a new parent. Rename needs to take the logs of both parents to ensure atomicity. This order has the following design considerations. First, it should be defined between any two directories, even unrelated ones. Second, to avoid circularity, this order must be transitive with parent-child order. Third, if we need to consider concurrent renames, it becomes increasingly difficult to make the order transitive. Let's see the simplified code for the solution of livelocks. If the two directories are the same, we acquire only one lock. In the case they are different, we acquire a profile system lock, rename mutex first. This simplifies the corner cases caused by concurrent cross-directory renames. Then, if one is an ancestor to another, to be consistent with the parent-child order, we acquire the ancestor first. Otherwise, the order does not matter, so we can choose the default order, namely old parent before new parent. Unlike the parent-child order, this order cannot be defined based solely on file system state. For instance, consider these two invocations. They operate on the same file system state, but will exhibit different wasteful order. To encode the order, we leverage ghost state, a commonly used verification technique. Ghost state only exists in the abstract model to assist the proof. We choose to update the ghost state before line 12 to represent the upcoming wasteful dependency between the old and new parents. After having acquired the two locks, we clear the goal state. The layer of an inode is now defined as the longest distance from root in the wasteful graph. For instance, in the left file tree, as goal state indicates a wasteful dependency from A to B, B's longest path to root is now 2. We can do the same to the other invocation. The goal state is a global unique value, so at most one wasteful dependency may be added to the wasteful graph, which does not conflict with the parent-child order. Therefore, the wasteful graph is still acyclic. With the layering strategy, we verify RefFS, which is a concurrent in-memory file system running on fields. RefFS leverages reference counting to achieve highly concurrent traversal. Simply speaking, reference counting prevents use out-free by increasing a reference counter. Only when the counter becomes 0 can the resource be freed. Unlike lock coupling, this approach does not always hold a lock in hand, therefore allowing concurrent operations to bypass each other and creating more parallelism. We apply our approach to the Linux virtual file system. We extended the previous layering specification to account for all inode locking orders. Surprisingly, we uncover a serious flaw in a recent version of the locking scheme. There used to exist two orders between directories, namely the parent-child order and the order between two unrelated directories protected under rename mutex. A Linux patch additionally locks the source subdirectory in a rename. For a non-cross directory rename, this introduces a new order between source and target subdirectories that is not protected under rename mutex. The patch's approach is to lock unrelated directories in increasing address order. However, address order is not transitive with parent-child order. For instance, a larger address parent may wait for its child. We have constructed a deadlock bug. You can see our paper for the detail. This bug was confirmed and fixed by the maintainer, and we also proved the fix correct. It needs to be mentioned that the Linux documentation has a contradiction proof of the locking scheme. The proof roughly goes by, if deadlocks are possible, there must be operations waiting for each other. By enumerating all such operation pairs, it concludes the proof by showing that such pairs cannot exist. There's no denying that the proof is detailed, but it lacks intuition, therefore still failing to catch the bug. To ensure such bugs won't happen in the future, we submit a proof patch to the Linux documentation. In this patch, we formally define the locking order that the locking rules wants to enforce. If someone wants to change the locking rules, they would be forced to come up with the corresponding order that justifies deadlock freedom. Such a formal specification would be effective in finding and preventing bugs, as shown by our experience. Next, we evaluated the proof effort and the performance of RefFS. The Moli framework uses our prior framework for C language support and concurrency reasoning. Moli mainly adds support for liveness. The RefFS also reuses the internal functions of AtomFS, but leverages reference counting for past traversals. The proof ratio of RefFS is about 80:1, which is lower than AtomFS, even when we additionally prove liveness. RefFS achieves our better performance than AtomFS because reference counting provides more parallelism than lock coupling. RefFS has also performance than commodity file systems such as ext4, due mainly to the lack of fine-grained optimizations. This talk has not covered some topics, including more formal details of Moli and the proof of RefFS, so if you are interested, you should check our paper. In summary, this work presents the Moli framework, which verifies the liveness based on a cyclic wasteful graph. We apply Moli to build the RefFS, which has a proof of both safety and liveness. We further apply our approach to build a proof for the Linux VFS. We believe the methodology of this work is applicable to other domains. You can find more information at the following site. Thanks for listening, and I'm ready to take questions.